Hello, everybody. Welcome to the downstream processing in biotechnology and separation, bioseparation processes. For this, we will continue the precipitation. Previously, I will talk like the first technique is PI precipitation. For this technique, we call it salting out precipitation. Salting out precipitation, that means we add some salt to the solution, and this salt will increase or decrease. But if the increased solubility, we call it salting in. For sorting out, it decreases the solubility of protein, and then protein can separate out by the precipitate form. That's right. In aqueous solution, that biomolecule writes protein or a film of water hydration layer at its surface with cover hydrophobic paths of the protein. That's right. If we can remove a water from protein, we make the hydrophobic path exposed to the protein surface, and exposed hydrophobic path interact intermolecularly, result in protein aggregation. That's why because the hydrophobic in the outside of the surface, that's why, and then we make protein aggregated for that case. This is a technique to precipitate protein. That's why the effect from adding salt into biomolecule solution, we call like the salting out and salting in. We have two kind of the effect. For the salting out, we call it hydrophobic effect. Cosmotrophs. For this case, water structure maker. For this case, what is a maker structure? For this case, increase surface tension of water and in water away from biomolecule. That's right. The solubility of the biomolecule decrease with increasing salt concentration for this case. For salting in, we call it the electrostatic effect. Cauchochoke. For this case, the water structure is breaker. That's right. Promote dissolution of biomolecule. For this case, we add some salt, it break the water molecule. That means it can dissolve more and more in water. That means overall solubility of the biomolecule come from a combination of salting in and salting out. That's right. For this case, show you right the effect of salting in and salting out. For the salting in, we call that if we increase some salt, we add some salt, the solubility, that's right, solubility. This is solubility will increase with salt concentration. Okay. And also, this is the salting in effect. And the salting out effect, if we increase the concentration of salt concentration, the solubility will decrease. That's right. But finally, in the normalized solubility, we get in the initial concentration of salt, there are some salting out or salting in effect. And then when the increase in concentration more, the salting out effect occur for that case. The combination of the salting in and salting out effect on soluble protein in aqueous solution. That's right. Low concentration of salt, okay, is indicate salting in. High salt concentration indicates salting out phenomena like this. And also for the real system, for this picture, show you the effect of salt. Yes, this is the effect of sodium chloride. Mostly the sodium chloride has the salting in effect because most of when we increase the sodium chloride concentration, solubility will increase. For this case, the log solubility divided by the concentration with no salt. That's the solubility. Increase with salt concentration, and there is some constant as about 1. For this case, the concentration of salt we determine based on isoelectric constant SI constant. Okay, for potassium chloride like this, and also moderately increase and constant for some periods of I, and then it will decrease at higher I. And for another, right, to ammonium sulfate and sodium sulfate, we can see that it's a mixture of salting in and salting out. Initially at about 1, that's right. The solubility increased with salt concentration increased, and then when we increase further the concentration of salt or I or isoelectric, that's right, ionic strength, or that's it, ionic strength. To increase ionic strength in terms of concentration of salt, the solubility will decrease for ammonium sulfate and sodium sulfate. That means sodium chloride and potassium chloride is not the best precipitating agent because it increases the solubility. But ammonium sulfate and sodium sulfate is the best choice for the precipitating agent because it can reduce the solubility of the protein. This is the solubility of hemoglobin as a function of ionic strength or concentration of the salt. Like this. As in the case of precipitation, we can suggest heuristic for shooting salt. The first one, the anionic salt are effective in following order for anionic salt. Okay, citrate is higher precipitate for this rank. The least precipitate is nitrate. That's right. The precipitation phenomena is citrate is higher than phosphate, higher than sulfate, higher than acetate, chloride, and the milk. The lowest is nitrate. This is the length of the anionic effective for the salting out. That's right. And for cationic are effective in the following order, like ammonium ion is effect for the precipitating higher potassium and higher than sodium. That's right. We call it step 1 and step 2. We call like lysotropic series or homicide series for that. For the first two, we call like the lysotropic series or homicide series. And also, we have another example right, for anionic. For this case is salting in. This case is salting out. Salting in, if we add it, the solubility will increase. For salting out, solubility will decrease. For this anionic. Or the Roman chloride, something like this. And this is for cationic. Ammonium ion is the highest salting in. That's right. The highest salting in. And as the lowest, sorry, this is lowest salting in. That's right. Sorry. This is the highest, this is the lowest for salting out. That's right. The lowest salting out means the highest salting in. That's right. This is the highest salting out. This lowest salting in. This is the lowest salting in. This highest salting. Highest salting in is lowest salting out. Like this. Okay. And the number 3, you have to choose a salt that is cheap, or you will use a lot of it. That's right. And the number 4, choose a salt that so that density of the precipitate is different than density of solution. That's right. If we choose the salt is the density is low, difference between solid and solution is difficult to separate after precipitate. And this means you have to choose the density of precipitate, and density of salt is quite different. Right? Number 5, add a solid salt rather than a solid solution to minimize the dilution. For this case, if we would like to add some precipitating agent, we prefer add the solid form, not liquid form. If you add some liquid form, it will be dilute the solution. If you dilute, it's difficult to precipitate up. That's right. The interpolate between experiment using general equation like log solubility. Log solubility is equal to constant with constant multiplied by salt concentration. That's right. A is vary with temperature pH, but the value M is does not vary. For this case, the constant A it depends on temperature and pH, but M is does not depend on temperature and pH. That's right. This is the general formula for express between the solubility and the concentration of the salt. So we can obtain this from the experiment. If you vary salt concentration and then you measure the solubility, you can calculate A value and M value. Okay. Like, for example, if we use plot between log S, that's right, log solubility, and concentration, for this case, you get the slope is -2 -m. That's right. It is slope. And intercept is A for that case. You can calculate A and M if you know the experimental result of solubility as a function of salt concentration. Right. In general, the solubility of salt in water is given by the equation by the ionizable species like K plus and sodium nitrate plus something like this. K is the solubility product. K is the solubility product. It's a function of cation molecule multiplied by anion molecule, something like this. For sorting out protein, S is Pi. If you remember that Pi means the pH at the protein concentration is minimal or minimal solubility. That's right. Minimal solubility. That's right. Many of negative charge are like acetic acid COO minus and positive charge are ammonium ion. The counter ion of this protein charge will be dominated by those of an electrolyte. May combine with the protein to form a precipitate. Therefore, the final that we get like K, that's right. Solubility product is expressed in terms of protein concentration, that's right, multiplied by the positive charge molecule, concentration of positive charge molecule, and concentration of negative charge molecule. That's right. Power N and power is constant. And also the solubility of electrolyte can be expressed at the previous I show you. That is the log SP divided by H0 equal to Ki minus Ks. SP is the solubility of dipole ion at ionic strength. The solubility at ionic strength. SO is the solubility of dipole ion in the absence of sound. This means SO is the solubility of molecule of product in the absence of sound. SP is the solubility in the absence, in the presence of the sound, something like this. Ki is the sounding in constant. Ks is the sounding out constant. And you can calculate ionic strength by this equation. The ionic strength is the half of summation Ci Zi square. Ci is molar concentration of any ion. And Ci is the charge of any ion. At ionic strength, the sounding out effect becomes predominant and can be described empirically by log S equal to beta K dash Si. It is the solubility of protein. K dash Si is the sounding out constant characteristic of the protein. It depends on the protein and depends on the salt concentration and pressure, pH and temperature. pH is above the isoelectric point. And the constant beta, hypothetical solubility of the protein at zero ionic state. We call the beta is the constant or hypothetical solubility of the protein at zero ionic state. It is depend on temperature and pH. That's right. And also it minimum value at isoelectric. And okay, we can like we can combine between salting in and salting out. The salting out effect. This is also salting in. If we combine this equation 4 and equation 6, we get log SP equal to log S0 equal to Ks minus Ki. That means beta is log S4. Ki is Ks minus Ki. If we combine equation 4 in terms of this equation, in terms of this equation, we get this. Beta is also log S0. K dash S is also Ks minus Ki. Ki is the constant for sorting in. K is my constant for sorting out. That means we can express in this equation 4. Like this show you right the ionic strength or concentration that affect to the solubility. Like some protein, mostly ionic strength increase, solubility decrease, the sorting out. That's like this albumin C, myoglobin, something like this, hemoglobin, something like this. All of this depend on ionic strength. Ionic strength increase, solubility decrease. And sorting out constant Ks can be expressed in terms of sigma, omega, and delta. For this is the non-polar constant, non-polar contact area. And this is the molar surface tension. And we can the sorting coefficient. We can use this to calculate, and sigma is the surface tension. Surface tension can be calculated from the surface tension of salt, dissolved in solution, minus surface tension of pure water, gamma, the surface of Solution did it include salt? Gamma zero is surface tension, did it excludes of salt? That's right. M is the molar concentration of salt. You can calculate sigma. That's right. And then you can calculate Ks. That means Ks depend on the concentration of salt. That's right. Concentration of salt. And surface tension. So this is another example like precipitation, salting in and salting out effect. That's right. Mostly like calcium chloride, sodium chloride. So I talked you previously. That is the salting in. Like ammonium sulfate, sodium sulfate is the salting out effect. For this case, if you plot between log solubility and ionic strength, you can find the slope of Ks, that's right, not Ks, in the linear relationship. That's right, after the higher ionic strength, we can calculate the Ks for this case. And also, this is for the ionic strength, some protein. That's right, the slope is minus Ks, like this. And the analysis that dependent of protein depend on the temperature, solubility depend on temperature. It is deduced precipitation based on assumption that denaturization follow the first order chemical reaction. In this case, for the linear relationship, we can write dP by dt equal to K, pp is the concentration, that's like protein, dissolved in protein, the dissolved protein or concentrated protein dissolved in water. K is the constant, that's like its characteristic content. E is the activation energy for denaturization. This is the denaturization. That's like the denaturation or the degradation of the protein. It depends on temperature. We can express it in terms of kinetic equation in the first order, like this equation. This is also another example, like this PI. Okay, for this case, I will give you some calculation example, like salting out of potassium nitrate. For this case, we plan to make 1 liter 2 molar potassium chloride with 1 liter of S molar sodium nitrate. How much potassium nitrate will precipitate? For this case, we mix potassium chloride and sodium nitrate, and finally we get the potassium nitrate at precipitate in solid form. Okay, for approximate solubility product useful in this problem are KCl10. Potassium nitrate is 1.7, sodium chloride is 35, and sodium nitrate is 100. Each is given in mole per liter or square. That's right. Each imply an ideal solution, which is a significant approximation. Okay, for this case, if sodium nitrate and calcium chloride is we mix together, that's right. In solution, it will be ionized. Calcium chloride will ionize to be calcium ion and chloride ion. Sodium nitrate also ionize to be sodium ion and nitrate ion. That's right. For this case, calcium ion will interact with sodium nitrate ion to be sodium nitrate. For that case, to be sodium nitrate is the precipitate. That's right. From the problem statement, that's right. For calcium chloride, it's 2 molar. That's right. And nitrate, sodium nitrate is 8 molar. But we would like to get sodium nitrate. That's right. Sodium nitrate is 2 molar. It's 2 molar. For that case, is only 1 per 1. For this case, we get it is a half. Because X is the amount, that's right, is the mole of calcium nitrate precipitate. That's right, mole of calcium nitrate precipitate. Okay, for this case, we call it X divided by 2. 2 is the total. That's right. Total volume, because we mix with 1 liter of 2 molar Kl and 1 liter of S molar potassium nitrate. Okay, for this case, the X is the mole per volume. That's right. X mole per volume divided per volume, we get the mole. That's right. The volume is 2. And also this is the precipitate. And then this is the calcium nitrate, 2 minus X divided by 2, because we have 2 molar. And calcium nitrate is minus X. That's right. Because 2 minus X means the remain amount of calcium ion. S minus X means the remain amount of nitrate ion. all of this divided by 2 because divided by the volume of the solution. And then finally you get the product, like the solubility product K equal to the concentration of this, as I multiply by this, equal to 1.7 for potassium nitrate, as I for potassium nitrate, 1.7. And then you can solve for X equal to 1 mole potassium nitrate precipitate for this case. 1 mole potassium nitrate precipitate for this case. That's right. This is potassium nitrate. Sorry, this is something wrong. Okay, sorry. This is potassium nitrate. Okay, precipitate. Okay, the next example, right, the calculation for this by the experiment, we find that the solubility of the albumin is about 12 and 0.006 gram per liter at ammonium sulfate concentration of 2.5 and 3.5 molar respectively. What is its solubility at 3 molar ammonium sulfate? For this case, we would like to study the effect of ammonium sulfate to the solubility of albumin. Albumin. For this case, we know 2 point. That's right. We know 2 point, and then we can use the general equation that's log concentration or log solubility equal to A minus M multiplied salt concentration. For this case, for the first experiment, we know log concentration is 12, A minus M. Concentration of salt is 2.5. And the second data, that's like log 0.06, 0.006 for this case, sorry, 0.06, right, 0.06, and then equal to A minus M multiplied by 3.5. For this case, we have two equations and two unknown, that's right. Two equation and two unknown. You can solve for A and M. That's right. For A and M. Okay. And then the question is, what is its solubility at 3 molar? That's right, at 3 molar. And then you substitute A and M into this equation, you get the general equation. That means log protein solubility equal to 21.6 minus 7.65 multiplied by concentration of salt. For the question is about at 3 molar, you substitute 3 into this concentration. And then you can solve for protein is 0.26 gram per liter. For this case, if we increase concentration, as I add 2.5, 12, and 3 equal to 0.26, and 3.5, 0.006, that means will you decrease if you increase amount of sulfate. This means the salting out effect, because the salting out will reduce the solubility of the protein. Okay, that example for calculation, that's that. The data were obtained on precipitation of protein by the addition of amino sulfate. For this case, we use amino sulfate as the precipitating agent. The initial concentration of the protein was 15 gram per liter. At ammonium sulfate concentrations of 0.5 and 1 molar, the concentrations of the protein remaining in the molten liquor at equilibrium were 13.3, 13.5, and 5.0 gram per liter respectively. From this data, calculate the ammonium sulfate concentration to give 95% recovery of the protein at precipitation. Okay, for this case, we go back to the general equation for the log S equal to beta minus K plus SI. Or maybe you can substitute log S equal to beta minus CK plus C concentration, something like this. You can express in this SI. For this case, if we use the data, we have two data, like the previous example, and then you calculate the constant beta and K, yeah, something like that, and K SI. And K, this K, sorry, this K value. Okay, for this case, we use this equation. Use this equation, it should be K, sorry, sorry. Insert, the equation. Okay. Okay, there is no function. Okay, we can still try. Okay. Yes, okay. This is the k value, right? It is k that is also for this k that is previous. Okay. We know the data from the true point at 0.5 and 1 molar. That's right. You substitute C is 0.5 and 1 molar. The solubility is 13.5 and 5. That's right. 13.5 and 5. And then you can solve for beta and K. That's right. It's also K that does. Then you get beta equal to 3.6. K that equal to 1.99. That's right. And then you get the general equation. You get the general equation. So you get the general equation is log S equal to 3.6. Log S equal to 3.6 minus 1.99C. For this case, we would like to recover is 95%. The 95% means the protein remain in the mortar liquor or the solution is 5%. 5%, that means the final concentration of protein equal to 0.05 multiplied by 15. 15 is the initial concentration. Initial concentration. Because it is the solubility after the precipitation out, as this. And then you can concentration, like calculate the concentration at 1.95 molecular. 95 molecular. Okay. Previously, we talked about the precipitation by isoelectric point, precipitation by something else, and we can another technique by using the organic solvent. If we release protein, if you mix the organic solvent, it will be induce the interaction by protein. We get the application phenomena, something like this. This is keep right. It depends on the dielectric constant. Dielectric constant indicate the polar or non-polar, something like that. If you add some alcohol or ketone, with its lower dielectric constant and the reduce solvating power of solution. And for low dielectric content, solvent induce more precipitate because if you add some solvent that is low dielectric content, that means it's lower solubility, that means induce precipitation. That's right. That is water. For this case, the ethanol, propanol, acetone is quite low dielectric. That means it can induce the precipitation because it can reduce the solubility of the protein. And also we can utilize the non-ionic polymer. This gives you the example of non-ionic polymer like polyethylene glycol that affect to the solubility of protein. That's why when you add polyethylene glycol, the solubility is reduced quite rapidly as it affect quite clear. Like it's the same formula. Like the solubility is affected by K MK. You can calculate from I showed you already from previous earlier of this lecture. That's right. And molecular diameter for this is the protein. That's right. The protein of this effect of protein. It's clearly that when we increase the non-ionic polymer like polyethylene glycol, it's reduce solubility. That means indicate precipitation. This is for another example, right? This is the protein effect. That's right. Protein effect due to the molecular weight. That's right. As high molecular weight of protein, it build or reduce the solubility is rapidly than the lower molecular weight. This is the, if we can utilize the polyelectrolyte. Previously we talked about the non-ionic, but for this ionic polymer, like this molecule, is the ionic polymer with the charge in the molecule, can also reduce the solubility and then make the precipitation. For this case, if we add some polymer with protein, it's a polymer that's with ionic, that means the charge, the surface of the polymer have the charge, and also protein have the charge. And then we form the complex formation protein electrolyte complex. And then we have by aggregation due to the charge in the surface of polymer and protein. For this case, there's the aggregation process for opposite charge protein and polyelectrolyte, something like this. In opposite charge interact like this. And the last one is the affinity precipitation. This is different for the protein or electrolyte polymer react with protein. For this case, we have like the molecule, some molecule which have the ligand. For this case, we have that is protein. This is the polyligand. Some did in the ligand we have some charge that can interact or cross linkage between protein. This is the ligand. Ligand mean the specific charge. That's why we have the specific charge that can interact with a specific protein. And then the ligand protein binding we get like this. Affinity precipitation. That's the primary effect. The effect, that's right. For this case, the secondary effect. And for this, we have like the ligand and protein. The ligand, please remember that ligand is the specific surface ion or surface charge that can react or interact with the specific protein like this. Okay, for this, we interact something like this, interact like this, and also like ligand protein binding. And then finally, we mix together is the affinity precipitation. For this case, is the tail or head. Mostly the head is water soluble or hydrophilic. This is hydrophilic. That's right. This is hydrophobic. The hydrophobic aggregation, and then we get the protein precipitate. That's right. The example of ligand that used to precipitate the protein, for example, like cytosine, lectin, polyethylene glycol. Okay, for this, yes, I did the last slide that I gave you like the example of precipitation. Please remember that the precipitation is the technique to add some chemical. That's right, to add some chemical to induce the protein precipitate. Mostly we add some chemical to reduce the solubility. That's right, the solubility of the protein. The solubility of protein is reduced, and then you can easily to separate by precipitation. We can precipitate by and precipitating agent like salt, that's like non-ionic polymer, ionic polymer, or affinity precipitation. And also we can use at the pI. If we adjust pH until it reaches the minimum pH, that the protein is non-charged. We call this pI, the minimum solubility at pI, something like this. Okay, we conclude that we have salting out effect, salting in effect, non-ionic polymer addition, ionic polymer addition, affinity or ligand addition, and also adjust the pH. For this technique, we can reduce the solubility and then it make the precipitation process. Okay, I will stop for this lecture about the precipitation. Okay, thank you.